Okay, this is the class on crystal structure, basically on Bragg's law. And before we start with Bragg's law, we have learned about the structure of a crystalline solid, and it is basically made up of different lattice point, and those lattice point are filled with the same types of atoms or molecular arrangement, and that particular arrangement is called basis of the crystal structure. And not only that, as those lattice point or the array of points, they are repeated itself in the space, which generate the space lattice that has got some symmetry itself. Now uh, let us consider that some electromagnetic radiation, if that interact with the crystal, what is happening? We have learned that from our basic physical optics class that matter basically interact with radiation in different way. Some of them we have already learned, some of them we learned from our quantum mechanics class, that when a radiation, basically if that is light, that are incident on a matter, it has go through the different types of natural phenomena, which basically it may be reflect, it may be transmit, it may be scatter, it may be interfere, it may be diffract, or some of the part may be absorb, some of the part may be absorb and re-emission, which is known as scattering, elastic scattering. Some of its energy transferred to the constituent particle. And not only that, some quantum mechanical phenomena like photoelectric effect, Compton scattering, pair protection, etc., etc. So these are the interaction of matter with the light. As that means if light is incident on that matter, those types of phenomena are going to happen. Now, if the matter itself is a crystal, what happens? If the matter itself is a crystal, then it go through different types of interaction already, and we are using crystalline state because it has got a repetitive pattern. That means if we learn about a part of that particular thing in a crystalline form, then we can predict its behavior throughout the crystal, right? So that is our main motto, that in the amorphous material its behavior may change in different part, but in case of crystalline solid, as that is repetitive in repetitive index are present there, so uh, there will be this property will repeat itself. Now, if a crystalline solid that are interact with the matter, as that is the material, so it may go through this all types of process. Now what happens, as the crystal is made up of basically the same thing, that is molecule, atoms, electrons, etc. So the same phenomena happens for the crystal. It can reflect, it can transmit, it can interference, scattering, diffraction, absorption, re-emission, and all types of phenomena that can happen. But when we are going to inspect a crystal, inside and we want to go inside the crystal, that means we want to find what is basically present inside the crystal, we have to look into the crystal through a very powerful microscope, right? So that powerful microscope is not a regular optical microscope which we are basically using in our laboratory to inspect the different types of what should I say, the particles like blood particles, like tissue, the cell, etc. But the dimension of that crystal, that is of the order of Armstrong. So we need a type of what should I say, the microscope that can have a resolution of the order of that particular Armstrong. Okay, and now what happens, we know that the crystal, as it is made up of repetitive index or repetitive units, so some natural phenomena like diffraction that may be helpful to inspect the inside construction of that particular crystal, and that is basically Laue treatment, which basically gives me the diffraction of crystalline material by individual lattice point. Now, what happens when some electromagnetic radiation that are incident on the crystal? If electromagnetic radiation that are incident on the crystal, what happens that if the wavelength of that particular radiation is of the order of Armstrong, which is of course either an X-ray or uh, lesser wavelength than that of an X-ray, then what happens, the constituent electron that are basically absorb the energy of that particular uh, radiation, and when it absorbs that particular radiation, the energy of that such an electron that are moving about the mean position vigorously. Okay, but the energy is not that up to that extent that it can either transform into the heat, or it can change the constituent what should I say, constituent uh, particle behavior of the particular crystal, but it re-emit the radiation as it incident on that particle. So that particular phenomena is basically called the scattering of X-ray by some atom. Now this process, that is the Laue treatment of diffraction, and even the complex process which the electron or the atom exhibit when it resides inside the crystal, that are basically very complicated. So a better understanding of this phenomena in the form of diffraction is given by Bragg's law. But truly speaking, Bragg's law is a combination of scattering and interference. Okay, so though I call this law as the diffraction, Bragg's diffraction, but it is basically scattering and the interference phenomena. Now let us proceed through uh, some pictorial description of crystal interaction of a crystal with that of a radiation. So let us consider that this is a source of an X-ray, which is X-ray tube. It is written here. Now this X-ray tube is moving towards some crystal, and we are using this filter such that we can use either a polarized X-ray, and we can just remove some of the unwanted wavelength the X-ray has. Okay, so using some suitable filter, we are just monochromatize the X radiation. That means its wavelength becomes unique. Okay, so what happens when this X-ray along this red line that are collimated and that particularly incident on the crystal, then what happens? Basically, it's scattered by the atom. But we are consider some planes inside the crystal. So the same phenomena in pictorial description, we can say that it is nothing but the reflection from a particular crystal. Okay, and that was detected by some detector. Up to this, everything is fine. Now the crystal has uh, several parallel planes. As it has got several parallel planes, so though this red line that is incident on the any of the crystal plane, it can penetrate inside the plane. Now there are lots of parallel rays that are coming and incident on the crystal. Now if each of this ray, some of may transmit through the vacuum, and some of the ray may interact with each lattice point. Now there are infinite number of planes inside the crystal. So what happens when X-ray is incident on the crystal? It is a probabilistic phenomena that each of that particular X-ray, and or rather I can say most of that particular X-ray, can be incident on individual lattice point, and that individual lattice point basically scatter that particular X-ray. So what should I assume this natural phenomena in a different way? That when this particular X-ray that is incident on the crystal, as this crystal have a several planes which having the mirror indices or the same mirror indices if they are parallel planes, then what happens? This X-ray that are basically reflected through this parallel plane, and as those reflected ray which are coming from the same plane, they do not have any, they do not produce any path difference amongst them. But if the rays that are coming from different plane, in the later portion I will show that if the rays that are coming from different planes, they are basically interfere either constructively or destructively depending on the path difference, and when it interact when it reflect or either interfere in constructively or destructively, depending on that we are getting either the intensity maxima or the intensity minima. So in this process we can have some of the spots in on the photographic plate, which we can see those spots appear due to this interference maxima points. Okay, and that particularly what happens as this photographic plate, it plays as a detector. So when the incident X-ray produce some interference maxima, what happens on the photographic plate, we are getting some spots, right? So now, why this X-ray? Look at this picture. Why not visible rays? So this is the spectra of the electromagnetic radiation. As you see here, this line is of the order of wavelength, and we cannot use radio wave because it has got a higher wavelength. Not a microwave, not infrared, and visible light, which have got of wavelength 10 to the power approximately 6 to 10 to the power 7 in this range. So that are basically greater than that of the dimension of the crystal. In that case, X-ray or the neutron diffraction, that basically plays a very good role for this diffraction. So if we want to see something which is microscopic, we need to interact with that particular system. And not only we need to interact with that practical system, we need to use some of the radiation, electromagnetic radiation, that can have a wavelength that is comparable to that of the dimension of that particular microscopic object which we are going to inspect. And in this case, as X-ray is an electromagnetic radiation, so it has got the wavelength of 0.1 to 100 angstrom. So that particular range of wavelength can emit of the dimension of the crystal, and the crystal dimension of course of the order of approximately 0.1 to 2 angstrom. So that small region can be inspected only by the X-rays or the lower wavelength than that of an X-ray. So we cannot use visible light for determination of that particular or inspect the crystalline material. So once we use the X-ray, as X-ray is electromagnetic radiation, so this is the picture of William Röntgen's wife when he placed his hand, and this is of course the ring in his hand. So X-ray is a good form of wavelength that we can use to inspect the material. Now, before the Bragg's treatment, let us say something about the historical background of this diffraction by a crystal. Look at the two pictures. In the left hand side, you can see the a round circle, and there are some black spots, and in the right hand side again once again a round circle, and you are looking for some black spots which I have taken from the journal, and that is basically the Laue photograph taken by Laue's assistant Walter Friedrich and Paul Knipping, and they are going to carry out an experiment on crystal diffraction. They have tried for the several times to execute this experiment, but they initially they failed to do that. But at lastly, on 23rd April 1912, they are succeeded to get this type of spot. But what is the significance of that type of spots? Basically, when which I am showing in my previous slide, that when this X-ray that are basically diffracted by the crystal, it uh, either produce some interference maxima or interference minima on the photographic plate. Now, if there exists a photographic plate and you are using a zinc blade crystal, and that zinc blade crystal is basically placed between some X-ray tube and a photographic plate, you were getting this type of spots. And for the copper sulfate, you are getting this type of spot. Okay, so depending on the, if you compare these two picture, you can see that depending on the internal arrangement of crystalline material, we are getting different types of different type of spot on the photographic plate. So these spots are basically characteristics of that particular crystal under our inspection. So these spots basically tells something about the natural phenomena, that is crystal diffraction. Okay, now this is the picture of three great scientists. At the left hand side you look Max von Laue, and right hand side there are two people who is just a father and son, W.H. Bragg and W.L. Bragg. In 1914, M.V. Laue received the Nobel Prize for X-ray diffraction, but in the later year 1915, Bragg's two father and son, they are receiving the Nobel Prize on crystal structure by means of X-ray. But what they have done, what Max von Laue done, I have just told you that Max von Laue treated a crystal as a lattice that were distributed on the space, and when parallel X-ray that are incident on the crystal, then each lattice point undergoes a scattering, and we are getting some scattering, we are getting some maxima when those rays are basically interfere either constructively. But the same thing, this complex process of scattering of some crystal lattice point, or scattering of X-ray or the electromagnetic radiation by the lattice point, is further simplified by this father and son. Initially, W.H. Bragg was experimented with these types of experiment, that is crystal diffraction. Later his son joined. His son received the Nobel Prize at the age of just 23. Okay, so he's the young Nobel laureate in the field of physics. And what happens when these two father and son join for X-ray diffraction, and they just told that this complex process may be simplified as we are considering X-ray as we are considering the crystal composed of different planes. Now, what happens when a crystal going through a electromagnetic radiation interaction? Now, as I told earlier, that interaction of X-ray with the crystal is a very complex process, and this process is described by the diffraction phenomena. But if you strictly says it's a combination of scattering and interference. But what happens, this complex process can be oversimplified by this Bragg treatment. Now what happens, say these are the parallel X-ray and you are giving a black box here, which means this is a crystal. You don't know what happens when the electromagnetic radiation just incident on that particular black box, and you want to look something which are coming from this black box, not really, this is the blue box, so that are coming from this blue box. Now what you get, you just use this X-ray which is incident, and you are getting some X-ray. Nothing more than that. The X-ray doesn't tell you that, okay, I see some atoms that are residing inside the crystal. No. But what you get, you were giving some X-ray and allowing some X-ray to incident on the crystal, and you were getting some X-ray that are coming from the crystal. Nothing more than that. Now what happens? What is inside the crystal? Look at the picture. That is basically consists of some molecules, and those molecules are basically composed of some atoms, and those atoms have some electron cloud, right? So crystal lattice consists of atoms, molecules. Those molecules can have some atom, and those atom can have some electron cloud. So it's a very natural phenomena that when the X-ray that are incident on the crystal, it must interact with the electron cloud of the constituent atoms. So this is a very natural phenomenon. So when this X-ray that incident on the crystal, those X-ray must interact with these constituent particle which is rotating in my picture. So this is an organic molecule. You look at that is basically made up of either carbon, nitrogen or oxygen. But not only that, if there exists a big molecule like DNA, what happens? The same thing, the same phenomena happens when X-ray incident on some big molecule. So in the first case, we are told this is a micromolecule and this is macromolecule. The same phenomena, that is the diffraction and interference happens, or rather I can say, strictly speaking, it happens as scattering and interference. And when X-ray that incident on this complex atom, then they must interact with the electron cloud of the constituent atoms. So what happens when in the X-ray that is incident on an atom, they make electron cloud to move with respect to a mean position where this atom is situated in the undisturbed position. And when this electromagnetic radiation that is incident on the atom, it tries to move, or rather I can say it move the electron cloud of these constituent atoms, okay, and it becomes bigger. So it is not only becomes bigger, but the electromagnetic radiation which is incident on the neighboring atom, that uh, electron cloud will becomes bigger. So what happens? In this way, this electron cloud becomes bigger and bigger. So the movement of this charge, when the charge is moving, so what happens? It cannot have such energy that it just knock the electron outside the crystal. So what happens? Then it, as this charged particle such as electron is moving, so it's re-radiate the wave having same frequency. Okay, but what happens? As this crystal have some other effects, that is either the absorption or something slow, so what I should say, the emitted radiation becomes little blurred. So this phenomena, but the frequency is the same, only the intensity may reduce. So this phenomenon is nothing but the elastic scattering known as Rayleigh scattering. Okay, and the scattering wave themselves be scattered by secondary scattering assumed to be negligible. Okay, so if the scattering radiation that are scattered, so that part basically we are not considering. So these are the interaction of the electromagnetic radiation with the crystal. Now what happens when these rays are emitting from the atom? Now look at the picture. What happens? This is the wavelength of radiation, and this first wavelength that are incident on atom number 1. It set the electron cloud of this atom to move. And what happens? This movement of electron cloud may re-emit this radiation of same frequency. Now same thing happens for the atom which is sitting at the position 2. So this particular wave that are incident on the atom, it re-emits. Now when it re-emits, look at this picture, these two rays are basically in phase. So what happens? The intensity becomes maximum. Okay, and if in this picture, if you look at this picture, these two rays are incident on atom number 1 and 2, and again they are just re-emitting the rays. Okay, and there becomes out of phase, so they interfere destructively, so we are getting nothing from this. So from these two phenomena we can see that either the constructive interference or the destructive interference happens for this particular X-ray diffraction phenomenon, and from that we can have some information about the uh, uh, structure of that particular crystalline material. Now how could you see an object? In the left hand side you just see there is a microscope, and when this is the microscopic object, the visible light that is incident on the microscopic object, and this object, this light is scattered. Okay, and you have some lens which makes this object or this scattered light much bigger, and you will get this image. But we don't have something such microscope, powerful microscope in our hand to inspect the dimension of the order of Armstrong. So we need some super uh, supreme microscope or the super microscope that are constructed via X-ray. So what happens? We are looking into the crystal, we are looking into the material in optical microscope. In the same way we are looking some atoms, and this is the crystal, and X-rays are incident. We are having the photographic plate. We are doing some complex Fourier synthesis or some analysis here, that is mathematical calculation which is done by this computer, and this crystallographer who are basically studying this molecule can have the information about the constituent particles, how they are arranged, what is the value of unit cell, how this repetitive pattern exists inside the crystal. So this is the complex microscope that is made by using this particular X-ray, right? So if two rays that are basically incident inside the crystal. So what happens? They are interfere, right? And we are getting just diffraction spots here. Now we know about the Young's experiment, that when just uh, two rays that are coming from different parts of this opening, and they interfere with each other, they are interfere either constructively or destructively, and we are getting the particular diffraction interference pattern of these things. Now I have told earlier that these two father and son, they received the Nobel Prize, and at the first time I am told about this law, that is 2d sine theta equals to n lambda. And what happens? The Bragg considered that the crystal planes that behaves through, they are partially reflected the X-ray like a mirror. Okay, and the mirror is made up of just atoms, right? So it is an atomic mirrors that are partially reflect that particular X-ray. Now the phenomenon of diffraction that basically inspired Bragg, that when a crystal that is basically placed under some X-ray, it can diffract the X-ray. Now if the crystal is rotated through the angle phi, then the diffracted ray is also rotated by same angle to through an angle 2 phi. Though the same thing happens for the reflection by a visible light through a mirror. Okay, so we should call this as a Bragg reflection rather than a diffraction. In this description, the angle which we are using as theta in case of Bragg's law, that is basically complement of the incident angle, which is called the glancing angle, which applied in some geometric optical phenomena, right? So when X-ray that are basically incident on the crystal planes, what happens? This X-ray incident at the point B and this X-ray incident at the point C. Now the path difference between these two rays is basically this AB and CD, and these two paths have the same value. So there will be actually no path difference when these two rays are moving towards this direction. So we are getting constructive interference having zero path difference. But when this X-ray that are penetrating through this layer and incident on the second layer, it reflect back. So these two rays, this first and the second ray, which is passing through this crystal and reflected by the second layer, and the rays which are coming from this first layer, they can interfere each other. Okay, now if consider the incident angle, incident wavefront that are basically propagating through a vector, and we are using some crystal planes. So we are moving towards a analogy of just reflection by a parallel set of mirrors, and that reflection of an X-ray by parallel atomic mirrors, right? So now in this mirror reflection, the wavefront is also consist of parallel wave which have which form the same angle theta in all planes. Now what is the path difference between these two rays? The path difference is basically d h kill sine theta. Now uh, this the path difference of these two rays, if you consider, that will be, if this is d, then this will be twice d sine theta, if theta is the angle. So 2d sine theta equal to n lambda. This is basically the Bragg's law. Now look at this picture. This is the incident wave front, this is the reflected wave front. Now what happens, these rays are reflected. Now this is the path difference and this is the path difference. This is the path difference of first ray between this incident ray, and this is the path difference between two scattered rays. Now this delta is, if this is d, this path is d, then and this angle is theta, so this angle is also theta, so this will be twice d sine theta, right? So if this is twice d sine theta, then total path difference between these two rays is 2 delta. Okay, so this will be 2 dHKL sine theta. So 2 delta equal to n lambda means there is constructive interference and we are getting diffraction spots. But if there will be destructive interference, we are not bothered about that particular region. So if there exists a set of parallel planes, we are getting the diffraction. But here you look at this form, that 2 dHKL sine theta equal to n lambda. So this thing happens for the nth order diffraction. But for crystal, if you are using 111 plane and n plane, it has just they are the basically the same planes we are using. Only what is there, only this DHKL is n times d nh n k nl. So if n is some integer, so spacing of nh nk nl plane is much greater than that of HKL. So if we use the notation of DNH, DNK, DNL, only this order number will change. So in this same picture as 2d sine theta HKL equal to n lambda, and the same form happens for nth order plane, that is nh nk nl, and this will be 2d nh nk nl sine theta nh nk, that will be equals to lambda. So this is the basically pictorial description of what happens inside the crystal. Here you are using just the planes, but actually there exist some lattice points, and we are considering those lattice points are basically have the atomic mirrors, and these rays are reflected by this particular mirrors when they they are going for a constructive interference, when they are so these are basically atomic mirrors. So when these rays are going for the constructive interference, we are getting this Bragg's law. Okay, now this is the complete picture of what happens inside the crystal. This is the radiation scattered by this atom, which are sitting in this first plane, and these are the second rays which are coming and incident on the second plane atom, and it reflect back, and these two rays are basically interference constructively to give us the Bragg's law, that is 2d sine theta equal to lambda. So this is first order diffraction. Just now in this complex picture, you are getting a very simple form of this Bragg's law. but the form is not so simple, because when, say for example, these rays are incident, so these rays are incident on some crystal planes. Okay, these are three parallel planes which I am looking. But what happens when first ray reflect back? Then this ray maybe pass through the second ray, second layer, and it's getting reflected, and partially it may penetrate to third layer, it may reflect. But when some of this X-ray, some of this electromagnetic radiation, they are just incident on parallel set of planes, basically a mirror, and it penetrate only through few micrometer, then what happens? The rays are basically attenuated because its intensity becomes less. And not only that, when it penetrates through the layer to layer, the rays are basically refracted. So when the rays are basically refracted, we are not using any refraction phenomena to consider this Bragg's law. But if you consider the refraction phenomena, the form of Bragg's law becomes very, very different. Okay, so we are not using that particular part, that is not beyond the scope of our discussion. So this happens, look at this picture. This is basically the crystal, and the bigger crystal which we are using for diffraction, and these are basically parallel planes. We can consider this type of planes, we can consider this type of planes. So any types of plane that crystal have, that we are getting only some diffraction maxima or minima when the Bragg's law is satisfied. Okay, so in this picture you look at the left hand side, that what happens when we are considering either the red plane or this purple plane. Okay, so the rays that are basically diffracted, having the different direction, that's where we are getting different spots on that crystalline solids, but on the photographic plate. But the fact is that when these rays which are diffracted in different direction can have the constructive interference. So the Bragg's law may satisfied for any direction. So we are getting different spots here. So now thank you for your attention.